Hello and welcome back. In this video, we're going to explore the concept of span a little bit more. So let's just remember that the span of a set of vectors in some dimension. So if I have these n-dimensional vectors, n could be 2, so meaning I have vectors in 2 dimensions, or I have vectors in R3, which means I have vectors in 3 dimensions. And the span of them is basically if I put them together, if I scale them, and then put them together tip to tail, the question is where can I make it to within that space? So in 2 dimensions, we can, with 2 vectors that at least don't point in the same direction, we can make it to anywhere we would like. We'll look at that in a second. So when we scale and add, that's just saying that we're going to take a linear combination of those 2 vectors. So in a nutshell, when you hear the phrase linear combination, what we mean is scale and add. Scale and add. Now what that means geometrically is tip to tail. Okay, so that means that we're putting them together tip to tail after we've scaled them, whether we've compressed them down or changed their direction. Once we scale and add them, we're taking a linear combination. So let's take a look at a more basic example here. Let's say that we want to know what is the span of the set of vectors, we'll say 1, 2, and 2, 4. Okay, so what we're asking is, what are all the different linear combinations we can form? The first thing I want to do to investigate this a little more easily is to kind of represent these 2 vectors on the same graph. So 1, 2, 3, 1, 2, 3, 4. Okay, so the vector 1, 2, the vector 1, 2 is going to be this vector here that starts at the origin and terminates at the point 1, 2. The vector 2, 4, if you think about that, well, 1, 2, 4 is really just double of 1, 2. So 2, 4 is pretty much the same vector. I mean, if you take 1, 2 and you double it, you get the 2, 4 vector. So that tells me that these 2 vectors lie on exactly the same line. And so more generally what I could do here is I could say, hey, you know what? These 2 vectors are on exactly the same line. And well, that means that the only places I can travel to are any locations along this line. So this line has a slope of 2 to 1. So the span of these 2 vectors, I can go anywhere on the line y equals 2x. So as long as the y component is twice the x value, I can scale these all day long. So for instance, if I want to ask the question, is negative 7, negative 14 in the span of those 2 vectors? Okay, well what I have to ask is, is this guy going to be a linear combination of 1, 2, and 2, 4? So in other words, can I take some multiple of the 1, 2 vector, add some multiple of the 2, 4 vector to it, and end up at the location negative 7, negative 14? Well, you can probably see that negative 7, negative 14 is indeed on this line, and there are actually infinitely many ways that I can do this. And I can find that out that when I solve this system here, negative 7, negative 14, and I do my Gaussian elimination on this to get this into reduced row echelon form, I will get 1, 2, negative 7, 2, 4, I'm sorry, 0, 0, 0, 0, 14. Because if you think about it, these 2 equations are really the same line. So that's really what this is telling us, is those 2 vectors are on that same line. And there are infinitely many ways you could do this as long as x plus 2y is equal to negative 7. So one possibility, and this is a situation where we have those infinitely many solutions, this would be the case where x, if we let y be some free value, then that means x has to be equal to, let's see, negative 7 minus 2 times that value. And so, for example, if y is 1, then x would have to be negative 7 minus 2, which would be negative 9. So 1 and negative 9 would work, and we can just double check that that's in fact going to give us a possible solution, or a possible way in which we could combine those two vectors. And a really easy way is to say y equals 0. If y equals 0, then x is negative 7, which means just take negative 7 times the 1, 2 vector plus 0 times the 2, 4 vector, and that will put you out over here at the point negative 7, negative 14. Now, that's the case where, you can have two vectors, but you can only make it along a straight line. That's when they're going to be multiples of one another. Another case to consider is what we call the standard or the basis vectors in 2 dimensions. And these are kind of the easier ones to see, that if I look at the vectors 1, 0 and 0, 1, then those two vectors actually point along the two axes. So 1, 0 is the vector that points 1 unit in the x direction, 0, y component, and 0, 1 is the vector that points straight up 1 unit. And if I want to ask the question of where can I make it, so these are called the R2 basis vectors, or sometimes you'll hear standard basis, because there are many ways to be a basis for R2, but we'll talk about that later. Okay, so if I want to make it to any location, say out here, we'll just call this point x1, y1. Well, if I can find the proper coefficients, we'll say those coefficients are a and b. We're going to take a times the 1, 0 vector plus b times the 0, 1 vector. Can I make it to the point x1, y1? Well, as long as this equation really says, and there's nothing really to solve here because a times 1 plus b times 0 equals x1 is the same thing as saying a equals x1. A times 0 plus b times 1 equals y1 just says b equals y1. So as long as what really happens here is I scale the 1, 0 vector by x1 units, well, what that will do is that will stretch it or shrink it if the point were closer to the origin than the vector is long. If I scale this by a factor of x1, and then I, from there, take the 0, 1 vector by a factor of y1, well, that will give me exactly that point right there. So a multiples the 1, 0 vector plus b multiples of the 0, 1 vector will take me to the point x1, y1. So these span all of R2. And that's just a fancy way of saying that I can get to anywhere I want in 2 dimensions. So in the thing that we can conclude here is that if I have vectors that are in 2 dimensions in R2, then there's basically 3 possibilities, depending on how many vectors I have. If I only have the vector 0, 0, and we haven't considered this one because this is kind of the trivial case, but if I think about where I can make it to with the vector just 0, 0, well, I can't make it to anywhere. 0, 0 is just, it has 0 length. So no matter what I scale the vector 0, 0 by, I'm going to always end up with 0, 0. So if you have a hoverboard that can only go 0 miles east for every 0 miles it goes north, it basically means it can't go anywhere. So your span is nothing. Your span is empty. You have an empty span. You can't make it anywhere. The second possibility is that you can span a straight line if you have, well, one vector. One vector will allow you to travel along a straight line, right? So if that's my vector, then I can make it to anywhere that line extends to. But wait a minute, just because I have more than one vector doesn't mean I can make it anywhere off that straight line. If I have 2 or more vectors, but they both fall along the same line, like in our initial example here, then I can still only get to anywhere along that straight line. Okay, so It's possible to span nothing. It's possible to span a straight line. Or the third case is where it's possible to span all of R2. So consider the standard basis vectors, for instance, because those are easier to visualize, that you can make it to anywhere. But if I had more vectors than that, you might agree that these two vectors will allow me to travel anywhere I want in R2. But suppose somebody tosses in a third vector and says, you can also ride that mode of transportation. Well, that doesn't change the fact that I can still make it to anywhere in R2 that I want, because those two pink vectors suffice to get me anywhere in 2 dimensions. This third vector kind of just adds redundancy. So this guy here would be redundant. And we'll talk more about what that means in the context of linear algebra.